Okay, and so now we're going to talk about linear regression. And in linear regression, kind of the big idea is, so we've got, we see some data, and now we want to try to fit a trend line, okay? And so here, and there's kind of this question of like, what line is the best line? What is the best line to use to fit our trend line, okay? So what line is the best line to kind of explain the relationship? Okay, and so so I'm going to show you kind of two candidate lines here, and we can try to decide if one line is better than the other. Okay, so here I've got our kind of our fictional data set with the closets and bedrooms. So I've plotted them here. So that's one. So one candidate line is the red line, and then the other candidate line is going to be this one right here, if I can get it right. That one, okay? And we're trying to decide which line is better. And like we could imagine like other possible lines as well, and so I'll just kind of put this blue line, and we can we would probably say as far as lines go, like the blue one would not be a good candidate for a trend line, but both the red line and the green line look pretty good. How do we decide which one is best? Okay, so this this would not a good line. Like our eyes can tell us that already. Okay, but as far as the difference between the red line and the green line, what line is the best line to explain the relationship? Okay, so the way we determine what line is the best line is we are going to look at something called the residual. Okay? And the residual is the difference between what our model predicts, or basically what the line predicts. So I'll write it out here. It's the difference between an actual value and what our linear regression line predicts. Okay, so essentially it's, if we think back to what a residual was when we were talking about ANOVA, it was basically what was left over after we've accounted for the fact that the group means were different from the grand mean. Okay, and here it's kind of the same concept. It's what is left over after we've accounted for predictions made by the line. Okay, so the symbol for residual here is going to be E, kind of like an error, something that's left over, and it's going to be the difference between the actual value of y and our predicted value of y. Okay, so you can think of it as what is left over like a residual is kind of what's left over anyway, right? So what is left over after taking into account the prediction line. Okay, all right, so the red line the prediction line is going to be So we're going to say y hat to indicate that this is, according to the red line, the prediction for y is equal to 2x. Okay, so whatever x is, the number of bedrooms, then we predict that the number of closets will be 2 times that. So we would predict, if you had 2 bedrooms, we would predict 4 closets. If you had 3 bedrooms, we predict 6 closets. Okay? And then as far as the green line, the prediction there, y hat, is going to be 1 plus 1.6x. Okay, so that's what these lines are. Okay, and we're going to say the best line I guess I don't need to put it in quotes. The best line will be the line that minimizes the total squared residuals. Okay, and so sometimes you will call here linear regression called OLS for ordinary least squares regression, or sometimes least squares regression, because we're minimizing the squared residuals. Okay, so sometimes called ordinary least squares regression. Okay, or OLS. Okay, and O for ordinary because there are other methods like weighted squares and blah blah, weighted least squares regression, and I don't know, the other stuff where people have complicated the process here. Okay, so here, so let me see if I can just copy this stuff here. Okay, so we have this, and then, so you don't have to redraw it in your notes or anything. I've run out of space. And then what did I say? I said y hat here is 2x, and then y hat over here is 1 plus 1.6x. Okay? All right, so let's look at calculating residuals. Okay? So, so I'm just going to copy this. Okay, and then let's see. Okay. So I'm going to have a y hat under the red. Okay. And then we will have the residual for y minus y hat, and then we will have residual squared for the red line. Okay, so under the red line, we would predict a value of 2, a predictive value of 4, 6, and 8. Okay, and that's kind of what we see. And then the difference here is, there's no difference there. We have a difference of 2, a difference of -2, and a difference of 0. So our residual squared would be 0, 4, 4, and 0. So our sum of squared residuals would be, we add these up and we get a value of 8. Okay? All right, and so kind of to picture this, we can look at the kind of the distance between what is this called? The dot and the line, okay? And because it's, what we're saying is that at the value 2, I'm predicting that we would be at 4, okay? But in reality, I'm up at 6. So my residual is that, okay? At 1, I'm predicting 2, and I am at 2, so there's no residual there. At 3, I'm predicting 6, but in reality, my value is 3. And at 4, I'm predicting 8, and I'm at 8, okay? So we're going to draw this, and then I'm going to kind of draw a little square here to indicate that I'm looking at the total squared residual here, okay? So we're looking at the residual, and I square it, and the total area here, that total area is 8. Is that good? Okay, and then we can do the same thing with this green line. Okay, so let's, whoops, that's not what I want. Okay, so under that we have this, and so we're going to have the prediction according to the green line, and then the error according to the green line, and then we'll have the error squared. Okay, so according to the green line at 1, if my prediction is 1 plus 1.68, I would predict we would be at 2.6. At 2, I would plug in 3.2, 4.2. And at 3, I would have 5.8. And at 4, I would have 7.4. Okay? And so my error here, the difference, is negative 0.6, 1.8. Is that right? I think I'm doing my math correct. Okay, 1.8 negative here, and then 0.6 there. Okay? And then I would square this, and I would get 0.36, and then 1.8 squared is 3.24, and 3.24, and 0.36. Okay? And then so if I add all of these up, I get 7.2. The sum of squared residuals here is 7.2. And if I were to draw the little boxes, we would have something that looks like this, and I'm just kind of and it might be hard to tell with my picture here, but apparently the total squared residuals here, the total area there, is less than the total squared residuals over here. Okay, and so according to our criteria for picking the best fit line, this one is the better line, 7 point. Okay, so the total sum of squared residuals is 7.2, so this one is the better line. Because
does it matter if the line ever starts at 0 and you ever concerned with?
I'm sorry?
The line.
Yeah, so here the line starts at 0. Because if I plugged in 0 for x, I would get 0 for y hat. And over here the line doesn't start at 0, it starts at 1. Because if I plug in 0 here, I would get 1 for y hat. So is it okay that the line doesn't start at 0? Yes, it's okay. Okay? Yeah. Yes?
How did you find those equations, those lines?
Yeah, I picked them because I know where I'm going. So I specifically picked these. Because I think, if I just showed you these 4 data points, I think a common selection would be to kind of just pick the line that goes through this point and that point, and kind of connect them, the two extreme points. And it produces a pretty good line, a line where the residuals only, our total sum of squares residuals only off by maybe about 10%. That's pretty good for eyeballing a best fit line, okay? And I picked this line because I knew that this would be the best fit line, okay? And I know this is going to be the best fit line because, well, I'll tell you how, so we don't, we could try out like thousands of different lines to see like, and then have a computer calculate the total sum of squared residuals, and then try to find the line that minimizes the total sum of squared residuals. But that would be inefficient, okay? And so you can apply calculus to the problem, and you don't have to worry about this, but this is basically what other people have done, is they applied calculus to the problem. And in calculus you've learned how to like minimize a function, right? Or maybe, okay, well anyway, you could. And you would try to minimize this function of basically the squared residuals, the sum of the squared residuals, which is really because if you treat your data as fixed values, the sum of squares residuals is really a result of what you pick your prediction line to be, okay? And so you could try to find, how do I pick the prediction line that's going to minimize the sum of squares residuals, okay? And so other people have done this, and we get to benefit from their labor, because now we just have a simple equation, or simple formulas that tell us the best fit line is always going to have these properties, okay? So the best fit line will always have the following slope and intercept. Okay, and so we would say the prediction line. So this is, again, this is our prediction for y, and that's why we put a hat over y. Is equal to, and it's going to be b0 plus b1x, okay? And this is going to be the intercept and slope. Okay, so probably in algebra you learned y equals mx plus b. Here it's, we kind of turn the terms around and we put the intercept first and then the slope next, okay? And this is kind of an, the reason why we do this is because in more complicated regression, you might have like other variables, and you would have b0 plus b1x plus b2x2 plus b3x3 or something. Like if you have multiple x variables, multiple predictors used for y. Okay, yes, question? There's a typo? The best fit line will always have the following slope and intercept. Well, I'm missing a word. Okay. Thanks. Okay. We'll always have the following slope and intercept. It's like your brain plays tricks, and you've probably seen those things where they stick in the word the twice, but it's like at the end of one line and at the beginning of the other. Yeah, you don't notice things. They stick in extra stuff, and sometimes after you write for a while you don't realize things. Yeah.
No, I was just...
Oh, stretching. Okay. All right. So the slope, so the way you would calculate it, the slope will always be b1 is our standard our correlation coefficient times the standard deviation of y divided by the standard deviation of x, okay? And once you have the slope, you can get the intercept, b0, and that's going to be y bar minus b times x bar. So you always have to figure out your, b1 times x bar. You gotta always have to figure out your slope first, okay? And a consequence of this is that the best fit line always runs through the point x bar, y bar, okay? Guess I'll get rid of the parentheses here. Okay, so the best fit line always runs through through that point. Okay, all right, and so with the other, with our bedroom data, we had x and x bar, and I think we calculated these statistic values earlier, and then so the bedroom closet data. We said x bar was 2.5. Y bar was 5, the standard deviation of x was 1.291, and the standard deviation of y was 2.582, and we calculated the correlation coefficient to be 0.8, right? So we had those data points, and then we could calculate these summary statistics. Okay, and so I knew where we were going, and so that's how I picked out our line of best fit. So if we want to calculate our slope would be r 0.8 times the standard deviation of y, 2.582, divided by 1.291, and this should be 0.8 times 2, and I get a slope of 1.6. Okay, and then our intercept is going to be y bar 5 minus the slope of 1.6 times x bar 2.5. Okay, and so this gives me 5 minus 4, and it gives me an intercept of 1. Okay, so my b1 is 1.6, my b0 is 1, and so putting them together into y hat is equal to b0 plus b1x gives me y hat is equal to 1 plus 1.6x. Yes?
And this works every time? It gives you the best fit line?
This will give you the best fit line according to ordinary least squares. Okay? And again, but it's important that you only use this if the relationship appears to be linear. Okay, if it's curved, it's not going to be good. Okay, but yeah, if it's linear, then yes, this will always work. You just need the mean of x, the mean of y, the standard deviation of x, and the standard deviation of y. Okay, those are very straightforward to calculate, and then you would need the correlation coefficient. Okay. And so, we learned how to calculate the correlation coefficient here. We said you find the z-score of x, z-score of y, multiply those together and add those up, and then divide by n minus 1. But in truth, nobody really calculates correlation coefficient by hand. It's just, for 4 data points or 5 data points, maybe it's easy enough, okay? But even then, it starts to feel a little tedious. But, you could imagine having a data set with thousands of data points. Okay, you would not be doing this by hand. Okay, and in fact, you would just throw it at the computer and say, "Computer, give me R," and it would calculate it for you. And then you probably, if your computer can calculate R, it will certainly be able to calculate your linear least squares fit line, and you'd say, "Computer, find the line," and it just uses this. Okay. It's not trying to do anything complicated there. And that would be it. Okay. Let me talk about kind of the interpretations of the slope and the intercept. Okay. So So the slope is the amount we predict, and it's a key word that we throw in predict, y to change if x is increased by 1. Okay, and so, you know, and then, so we had for the, our bedroom closet, we said y is number of closets, and x is number of bedrooms. And we had y hat is equal to 1 plus 1.6x. Okay, and so this means is that if one place has one extra bedroom compared to another, okay, so that this is the part where we increase x by 1. Okay, then we predict it will have 1.6 more closets than the other. Now, of course, in reality, you can only have 1 more closet or 2 more closets. Okay, you can't have 0.6 of a closet. Even if it's a small closet and you don't feel like it deserves the title closet, it's either you count it as a closet or you don't. Okay, so we predict it would have 1.6 more closets than the other. Right. Do closets always have doors? Maybe. If it doesn't have a door, it's called an alcove. Is that? Yeah. I don't know. I don't know. And then if you have a closet in a kitchen, is that just a pantry, or is that, can you have a closet in the kitchen? So is a pantry just a closet in a kitchen?
No, like shelves, right? That don't let you put.
Well, you can have shelves in any closet.
You can get really creative. You can put all your shirts in the pantry.
So,
They're nice.
yeah. It's kind of like trying to define a sandwich, right?
Yeah.
It's like when is like a hot dog is not a sandwich, but you know, like when does something, like, because you'd say like, oh, it's something, you know, something in between bread, but then it's like, well,
That's not the right way.
but yeah, exactly, right?
It's tubular meat.
You know, if you put a pizza on top of a pizza, and that's not a sandwich, right? Or do you remember the KFC Double Down?
Oh gosh.
Is that technically a sandwich? Yeah, okay, anyway, this is like things are hard to define. Okay, so anyway, if we increase x by 1, we predict this will have 1.6 more closets than the other. So it's the amount you predict y to change if x is increased by 1. And so it's not necessarily that y will change, okay? It would be incorrect to say if we increase x by 1, if we add a bedroom, we're automatically going to get 1.6 more closets. That's not true. It's just overall our prediction based on our data changes by this, okay? Okay, and then as far as the intercept goes, this is our prediction for y. If we can set x equal to 0, okay? Now, in some cases, you can't set x equal to 0. So this would be, you know, if a place had 0 bedrooms,
Studio?
yeah, you know, I guess like that's what it means to have have 0 bedrooms, right? But technically, it's the place is just a bedroom, right? But yeah, we only call it a bedroom if I guess it has a door that's not the door that goes to the outside. But if a place has 0 bedrooms, we predict it will have 1 closet, according to our model. That's what we have here. It's all kind of, but in other cases, we would have like different models here. Okay, so let's say x is we take a woman's height, and then y would be her mother's height. Okay. Okay, and so we're trying to see if a woman's height is related to her mother's height or something like that. Okay, and I'm going to just completely make up numbers here, so I have no idea, right? So I might say like y hat is 28 plus 0.56x. Oh gosh, this is, I don't even know if this is like even remotely true. Okay, so now I'm too curious if wait, hang on. Oh, okay, yeah, I guess this actually isn't so terrible. This model I made up.
So it's not like.
Okay, so yeah, like if you
Won't be an Amazon compared to your mom.
yeah, no, okay, so I mean, so I've just said like, okay, what if a woman is 5'5" according to the model, or if we predict her mother would be 5'4", so it's like I'm surprised. All right, okay. All right, so anyway, according to this, if we increased a woman's height by 1 inch, or or a better way is like if we had one woman who is 1 inch taller compared to another, we would predict her mother to be 0.56 inches taller than the other mother. Okay. I don't know if I have to write all of that out. Okay, and then and as far as the intercept goes, it would be our prediction if we set x to 0. Now this is where it doesn't make sense. Like if we plugged in 0 for a woman's height, that's a person that doesn't exist, right? You can't have a height of 0. And so we would predict said person to have a mother who is 28 inches tall, but that doesn't make sense either. So in certain circumstances, it makes sense. You can plug in x equal to 0, and in other cases, it does not. But yeah, this would be, if we were comparing one woman to another, and one woman is 1 inch taller than the other woman, we would predict that woman's mother to be 0.56 inches taller than the other woman's mother. Okay, so we have that. There is this concept of r squared, okay? Okay, and this is called the coefficient of determination. All right, and it's like a fancy word for, I don't know. Okay. It's the amount, the definition of this is the amount of the variation in y, that can be explained by the variation in x. Okay? So the amount of the variation in y that can be explained by the variation in x. What does this mean? Okay. Or actually, it should be the variation in the model, but for linear regression, the model is just x, really, okay, because we only have one predictor. For linear regression, capital R squared is just equal to the correlation squared, okay? So in linear regression, it's a very simple relationship. You take the correlation, you square it, and you get the coefficient of determination, okay? In more complicated regression, this relationship is not so simple, okay? But for linear regression, this works. Okay, so what does it mean? The amount of variation in y that can be explained by the variation in x. Okay, so let's go back to this x being the woman's height. And y being the mother's height, okay? And actually, it probably, you know, just for this one, let me switch the labels of x and y, okay? But, yeah, you were gonna...
Can we go over that equation again? I'm really worried about that.
What, the
So,
28 plus 0.56x?
yeah, 28.5.
Yeah, okay. So I'm gonna just say y is the woman's height, and this time x will be the mother's height, and I'm just, I don't know, so we'll say y hat is equal to, now I'm just going to change it up a little bit, 29 plus 0.56x or something like that. Okay, I'm again, just making stuff up. Okay, wait, so what's the problem here?
So, I mean, I know it doesn't make sense for a woman to be 1 inch, but then if she was 1 inch, then her mother would be 20. Well,
In this case, 29.56 inches, yeah.
Okay.
That's
Just making sure.
yeah, that's what this thing says, okay? And I'll talk about why that doesn't sound like correct, and it's not correct to use it in that sense, okay? All right, so here you were saying, okay, if a mother's height is something, you know, so we predict, like, if x is equal to 60, you know, we predict y hat is, and then we would plug in 60 times 0.56, it would be 29 plus 0.56 times 60, and I don't know what this is, 60 times 0.56 plus 29, we would predict 62.6 inches. Okay, so this says, you know, if a mother is 60 inches tall, we predict basically her daughter to be 62.6 inches tall, or something like that, okay? So, you know, we're just making this up. I can say, you know, maybe r between x and y is like 0.58 or something like that, okay? So again, I'm just making up these numbers here, okay? So then our r squared would be, you know, like 0.3364, okay? So 0.58 squared is equal to 0.3364. Okay. All right. So what this says is that basically 33.64% of the variation in y can be explained by x. Okay, so what does that mean? All right, so we can think of, you know, what are the factors that go into determining a person's height? Okay, what are the things that influence how tall someone ends up being?
Nutrition.
Yeah, so nutrition, genetics, so those are probably the two biggest things, right? But then, like, do they have a nice bed? Like, these things also play into a factor, right? And you know, do whatever stuff, you know, how much exercise, or like, do they have to carry heavy things on their back, or I don't know, just like there's lots of different things that could go into, you know, or like, you know, did they have, I don't know, some kind of scoliosis or something, right? So as far as like, and not just like genetics on your mother's side, but genetics on your father's side, and all sorts of stuff, okay? So there's all sorts of things that go into determining how tall someone ends up being, okay? And so what this says is that about 33.64% of how tall someone ends up being, okay? Rather than just saying, well, everyone's different and some people end up tall and some people end up short, we can say, like, according to this information, about 33.64% of that can be explained by the mother's height, okay? So if we know how tall the mother is, we can explain about 33.64% of this variation, okay? And the interesting thing is that the flip, the inverted relationship is also true. So then we can also change it around and say 33.64% of the variation in the mother's height can be explained by the daughter's height, okay? And that sounds weird because we feel like there's this causal relationship between the mother's height, x, and what happens with the daughter. But it's, with correlation, the direction of the causation is not implied at all. We're not, just because x and y are correlated doesn't mean x causes y, or that y causes x. So the direction actually doesn't matter. And so what we're just saying is that when we look at the numbers, and we see, mothers have different heights, we can explain part of that by looking at the daughters that have different heights and things like that. So we're going to say basically 33.64% of the variation in y can be explained by x. And at least for linear regression, we can switch that around, and we can say 33.64% of the variation in x can be explained by y. Okay, so we can say, 33.64% of the variation in a woman's height, or in, not a woman, it should just be women in general, in women's height can be explained by the variation in mothers' heights. Okay, so that is the coefficient determination there, okay? Okay, so then I have to end this chapter with kind of like warnings about correlation and causation and linear regression and all of these things that, like, don't do. Okay, so linear regression is, or just regression in general, is a very powerful tool, and it's very widely used, partly because you can do a lot with it, but then also because I think it's relatively easy to understand as far as different statistical methods go. But it also makes it easy to be misused, okay? So a few warnings, okay? Number one, make sure the relationship is linear, okay? Is linear, or at least reasonably linear. Okay, so that's very important. Another one. Okay, so beware or be aware of outliers. Okay, and so as they can dramatically affect the results. Okay, and so let's say you surveyed a bunch of people, and you asked, what shoe size do you wear? And then you ask, what did you score on the SAT? Okay? And what kind of what is the R value that you would expect?
Zero.
You'd expect 0, right? You would have people wearing big shoes and small shoes, people with high and low SAT scores. So you would have, you know, shoe size and SAT. Okay, and so you'd have R equal to 0. Okay. So this is like normal people, right? What if Shaquille O'Neal had taken the SAT and he got a perfect score? So let's say his dot would be out here or something like that, okay? So what before the relationship would have been 0, you would have had kind of like no trend. Now, if we include Shaquille O'Neal with his very big feet, now the trend would suddenly appear like maybe there is maybe there's a trend between shoe size and SAT or something like that. Okay, so the presence of such an outlier can influence this. Okay, and the value of correlation. So, sorry, I should say R is equal to. Oops. So under with the red line, R is equal to 0, but then with Shaquille O'Neal, maybe R suddenly, it doesn't even have to be a dramatic change. R might be equal to like 0.1 or something like that, 0.1, okay? But this is enough to start influencing, now you think there's a relationship or something, you know. If you've got enough data points, this could be significantly different from 0, or who knows, all right? So it could affect your results. Okay. Another warning, do not use your regression to make predictions in regions where you have not collected data. Okay, and so here's a silly example. Okay, let's say you are recording your child's height. Okay, and maybe you record how tall your child is. Every twice a year since let's say he was 3 years old or something. Okay. And now he is 11, okay, and so every time you've measured his height, he has grown, okay, and so this is at age 3, and now at age 11, and he has grown from whatever to like 3 feet tall to now 5 feet tall or something like that, okay, and then so you say, oh, well, at this rate, by the time he is 55, he will be 16 feet tall or something like that, okay? Like we laugh and we say, oh, that's ridiculous, right? But people do stuff like this for other things that we're less familiar with, and so such predictions don't seem as outlandish to us, okay? Because we're less familiar. So, and the thing is the truth is in that we know that as far as heights go, it kind of like you reach a certain point and you stop growing, and then maybe in your old age your bones shrink and things like that. But something like that happens. But it would be very silly to try to project this and say, by the time my son's 55, he's going to be really, really tall. But people do this all the time. They say like, oh, from 1980 to for the last 30 years or something like that, we started measuring this thing since 1980. And we have seen this trend, and so that means by the time 2050, this is what things will look like, and it's terrible, or something like that. And the truth is we don't know if the trend that has existed over the past 30 years will continue on for the next 30 years, or if it will go up dramatically, or if it'll level off. Without maybe, just from the data, we can't do that, okay? If we have a scientific understanding of some of the underlying processes, then we might be able to say these things will continue in this direction, or these things will, because of the scientific process, we know it's most likely to start becoming exponential, or maybe it'll level off or something like that. But if we're just looking at the data without an understanding of underlying processes, it's very dangerous to try to say this trend will continue on into the future forever, or things like that, okay? But I think a lot of people, maybe unintentionally, not with malicious intent, but start making predictions as such, okay? And we always want to know what's going to happen in the future, but the truth is the future is very hard to predict, if not impossible, okay? So, I mean, even like we can think of like politics, and like what's going to happen in 6 months, or not even like 5 months in November, and stuff like that. And people are trying to predict like how things are going to go, but we really don't know, right? Like 6 months ago, I don't know if anybody would have predicted what we're seeing today. So who knows, right? So yeah. So the future is very hard, and anyway, so just don't do this with regression, okay? All right. So I'm trying to think. Are there anything else I have to say? No, that's about it. Are there questions, or? Yeah. No. Okay. All right. We'll end here, and so next week we'll spend mostly in review, and that will be it. Have a good night.